Hello again. I've been asked to put together a video based on Chapter 11, Design of Beams and Shafts. So let's get to Chapter 11, review a few things, and then we'll work a couple problems. Here we go, Design of Beams and Shafts. Okay, the key thing here is that we are going to be looking at existing beam sizes and shaft sizes. And so we're going to be able to look up their material properties, or their section properties rather, in a table somewhere. The shaft's a little different. We'll have to calculate a diameter, but then diameters only come from the store in certain sizes, and so we're going to round up to those sizes. We decided that we want to use this equation for prismatic beam design, right? And so we said that bending, for the most part, is going to take precedence over shear. So let's review what we mean by that. Right? We said that first we defined S. Remember this? We said S was the section modulus. And we said that S was equal to I over C. Remember, I is the moment of inertia. And C is the maximum distance from the neutral axis, right? Or the centroid, right? Now, maximum distance. If you have a symmetric section, it's always the same. But if it's not symmetric, then it's not the same. Let me see if I can get a bit less. That's a little better, huh? Okay, so then we said that for bending stress, right, it's MC over I, which is saying it is basically M over S, or that leads us to S is equal to M max, and this is a max, of course. When we use C, we get a max moment. It's M over sigma allowable. So this is the equation we want to focus on right there. Okay. And so what that's going to allow us to do is, given a moment and given a stress allowable, we're going to be able to define the cross-section of the beam. And we're just going to look up the answer. Just look up the answer. Because we're dealing, as I said, with existing shapes. Now, sometimes you may actually have to design the beam, but what we're going to focus on is ones that we just look up. Okay, so then we still have to check for shear. We still have to check for shear stress. And the reason is, for long beams, right, bending stress rules. But for short beams, that should be an S, shear stress rules. Now, define long and short. I can't. But the point is, for the most part, we're dealing with long beams, and we're going to size it based on bending stress and then check for shear stress. And if shear stress comes out to be critical, then we'll have to resize the beam. We'll have to check it for shear stress. Then it's a short beam. Okay. Let's just do an easy problem here. Let's see, let me find an easy problem for us. We'll just take one of these fundamental problems in the book, okay? All right. Here we go. So we're going to look at this little fundamental problem. I think we'll do F11-3, all right? And this is determine the minimum dimensions A to the nearest millimeter of a beam cross-section to safely support the load. In this case, we're giving wood. Now, A is just the, see, this is like a 2x4, right? So it's 2A by 1A. But they give us an allowable normal stress of 12 MPa and an allowable shear stress of 1.5 MPa. So let's just write a few things down for this little problem. So we have a beam, and it's a simply supported beam, right? And we have 15 kilonewtons at 0.5 meters, and this is 1 meter over here. Okay. And the cross section of the beam, this is 2A by A. And we know that sigma allowable is equal to 12 MPa. And we know that the tau allowable is 1.5 MPa. And they're saying define A. Well, the first thing we need to do is find M, right? Find M. Find M. Max. We need the maximum moment. Now, there's a couple ways you could do that, right? You could draw a shear moment diagram. That would be helpful. But first, then, if we're going to do that, we need to find the reactions, right? So let's see. If this is 15 and this is 1 by 0.5, then we know that 1/3, see, this is 3/2, right? So that means that we're going to get 10 here, and we're going to get 5 here. So in other words, you sum up the moments about this point, but when you have thirds, it's just going to split. Oh, I did that backwards. Sorry. There we go. Yeah, the bigger load always goes to the shorter distance. Okay. Gosh, almost scooped that up. Okay, so we now know we have that. So let's do a little quick shear moment diagram. It's really easy to do. It's going to go up 10, right? Across, then down 15, and up 5. So this is 5, this is 10. So the moment is going to go up and then down. Well, what's the max moment? It's just going to be 10 times 0.5, or if you wish, 5 times 1. Same thing, right? They do have to match. And so the max moment is equal to 5 kilonewton meters. That was easy. Now, you didn't have to do a shear moment diagram. You could have just looked at it and said, oh, it's going to be 5 kilonewtons here, and 5 times 1 is 5, or it's going to be 10 here, and 10 times a half is 5. This is an easy loading, very straightforward loading, right? Okay. Now, what's the next step? So we got the moment. Now we got to find S. Well, we said that S is equal to M max over sigma allowable. So S is equal to, we'll just write it down, M max over sigma allowable, which in this case is equal to 5 kilonewton meters divided by sigma allowable is 12 MPa. So that's 12, right, times 10 to the third, no, 10 to the sixth, sorry, 10 to the sixth newtons per meter squared. Okay, so the newtons are going to cancel. That's good. One of the moments, so it's going to work out to meters cubed, which it should. So let's see, that's going to come out to that comes out to 4.17 e to the minus seventh, or 0.417, right, 10 to the minus 6 meters cubed. So one of the nice things about fundamental problems, when you work them, and when you're doing these on your own, the nice thing is you can always go to the back of the book and you can sort of look up the answers. So let's see how we're tracking here so far. They go straight to A. Well, we got the loads right. We got the moment right. They just went to MC over I instead of calculating S. Okay, that's all right. We can do that too, but let's do this process because I want you to understand the process for other things. So we'll still go back and check that answer. All right, anyway, we have an S. And we said that S is just, remember we defined it as I over C. Okay. The moment of inertia of a rectangle about its centroid is 1/12, right? BH cubed divided by C, and we know that C is 1/2 H, right? And so we remember that that comes out to 1/6 BH squared, because we've done that before. But just as a reminder. Well, in this case, B, right? B is the base, so that's A. So that's 1/6 A, and H is 2A squared. So that comes out to 1/6 4/6 A cubed. Okay, or 2/3 A cubed. I think that's what they got too. I should have left that page open. Let's see, 11-3. There it is, 2/3 A cubed. Ta-da! Oh, A to the 4th. Oh, of course it's cubed. No, they forgot to divide by C. Yeah, because C is A. Right, so we're good. We're good. So now we got to calculate what that is. So we said that C, right, was 0.417 times 10 to the minus 6 meters cubed, and that's got to equal to 2/3 A cubed. Let's see, so multiply by 3 to divide. Now we take the third root. And I get 0.00855 meters, right? And so that's equal to 1, 2, 3. Oh, sorry. That decimal point in our place. There we go. 0.855. And so that is 86 millimeters. And that's what the book got to. 86 millimeters. Okay? Now, we got to check shear. Got to check shear. Remember that? So now we've defined A. We got to check shear. We know that tau, right, is equal to VQI T. So we're going to take the top half. So this is a problem that y'all have had in finding Q. So let's just draw a little picture here of our rectangle. So we want the maximum shear, right? The maximum shear, let me write this down for you. Max shear is always at the neutral axis. Okay? So what's going to be the Q max is going to be equal to this area times this y bar prime. And this is A prime, right? So it's excuse me, A prime y bar, which is equal, or y bar A prime, same thing. So that's equal to, this is A, remember? And this is, so this is A from here to here. And A is, we said 86, right? Now we're going to use the number we picked, not the number we calculated. Because now we've said, okay, we're going to make it this big. So we're going to use that number. So we're going to say that we're going to have the area is 86 by 86. Oh, and this is millimeters, so let's convert that to meters. There we go. And we need a y bar. Well, our y bar is, guess what? 0.86 over 2. Okay. And so we punch that into our calculator. 0.086, enter. We're going to cube that, right? And then we're going to divide by 2. And we get we get a small number. 00032. Here, let's multiply times 10 to the 3rd. There we go. 0.318 times 10 to the minus 3rd, right? And that's meters cubed. Remember, we converted to meters here. So now we've got, we don't know, we have V. Remember V? Remember from our shear moment diagram? What's our maximum V? Our maximum V is 10, right? Oh, you can't see that. There we go. Maximum V from our shear moment diagram is 10. This is why we do shear moment diagrams, folks. It just helps us with the beam. Okay. We haven't, see, did we calculate I? No, we didn't calculate I. So we'll have to calculate I. I, however, we didn't actually run it, but it's 1/6. No, it's 1/12 the base, which is A, times the height, which is 2A, cubed. And that's, we said A was 0.86, right? And so the moment of inertia is going to come out to 36.47 times 10 to the minus 6th meters to the 4th. Now I have to admonish you all, watch your units. People are goofing up units, right? So be careful on your units. So do we have everything we need? So now we can say shear stress max is equal to V. Well, we got V, right? That's 10. That was 10 kilonewtons. Remember? 10 kilonewtons. So that's 10 times 10 to the 3rd newtons times Q, which is 0.318 times 10 to the minus third meters cubed over I, which is 36.47 times 10 to the minus 6 meters to the fourth times T. Well, in this case, T is A, right? There's no difference. T is A. So T is 0.086 meters, VQ over IT. Yeah, so let's just write this up here. T equal to 0.086 meters. All right, so what's the next thing we do? Now we just calculate that, and we'll find that tau is equal to 1.01 MPa, or Newton per meter squared times 10 to the sixth. And that's less than the allowable, right? Because we said at the beginning, T allowable was 1.5 MPa. So we're good. Now what if we had said, let's make that out of an existing shape. I don't know if we can make an I-beam that small, but let's do another problem. Yeah, let's find another problem. Well, let's look at F11-6. I know this was a homework problem for y'all, but let's do 11-6. That one, by the way, that we just did was 11-3. Right here, this was 11-3. Okay. So, here's the problem here, right? Remember that? It says select the lightest W410 shaped section that can safely support the load. The beam is made of steel, having allowable normal stress of 150 MPa and allowable shear stress of 75 MPa. Assume the beam is pinned at A and a roller supported at B. So we're going with pinned, and we got this 150 kilonewton load out here, right? So we'll replicate that. Here's our beam. We'll load out here. We got a support there and a support there. All right. So this is 150 kilonewtons. And sigma allowable is 150 MPa. And tau allowable is 75 MPa. All right. So first thing we do is find the moment. Oh, this is 1 meter. This is 2 meters. So we got to find the moment. The maximum moment. Once again, first thing we do is find the reactions, right? So we're going to have a reaction here, and we don't know the direction of this reaction. But if we summate some moments about this point, right, it's going to be 150 times 3 minus something times 2. All right, so 150, 3 times 2 divide. I get 225. That means this is going to have to be this way, right? So 225, 150 minus is 75. And these are all kilonewtons. And so what's our shear? So our shear, it's going to go down 75, go across here, then up 225 and across to here and down. So it's 150, and this is minus 75, right? That's the shear. And what's the moment look like? So it's going to be 150 times 1, isn't it? And that's that way. So this is going to be the other way. So it's still going to be so this is going to be 150 times 1, or M max is equal to 150 kilonewton meters. All right? And it's right here at B. And of course that's consistent. We know when we have a 0, because this is the slope of that, right? So you got to have constant slope and then cross section right there. I mean, it crosses right there. All right, so we got our max moment, and we have our shear allowable and our stress allowable. So we can calculate S. S is equal to 150. Yeah, let's review S. S is M max over sigma allowable. So S is 150 kilonewton meters over sigma allowable, which is 150 times 10 to the third kilonewtons per meter squared. So S is equal to 1,000, no, it's 0.001 meters, excuse me, 0.001 meters cubed. All right, so that's equal to 1,000 times 10 to the third millimeters cubed. So why millimeters cubed? Well, because now we go to the back of the book. Almost the back of the book. We need appendix B, right? Yeah. The appendix B. And they want us to use a W410. That was part of their requirement. W410. So here's I-beams, and these are wide flange sections, or W shapes, and this is in SI units, which is what we're in. So we come down here, we're going to pick a 410. And we need to have an S. I'll zoom on this in a minute. We need an S that is at least 1,000. Now note, let me zoom in on this for us. Ooh, that's a big zoom. All right. S is provided, and it's in 10 to the third millimeters cubed. Hence the reason we converted from meters cubed to millimeters cubed, and why we put the 10 to the third on there. It makes it easier to go into the table and get the right answer. So again, be careful with your units. Note that I is 10 to the sixth millimeters to the fourth. We're going to need that in a minute. Okay, here's S. So we need, here's our 410s down here. Gotta be sure I'm on the right section. You can't see the whole thing here. There we go. Here's our 410s. And this is our S column here. That's too big, that's too big. That's a little big. That's too small. So all the others are too small. So they limited us to 410s. looks like the only one that'll work is the 410 by 67. 410 by 67. Remember, 410 is the approximate height. In this case, it's exact, but you can see the family of 410s. And the number on the right is the weight per unit length. Well, in this case, since we're metric, right, it's kilograms per meter. In English, it's pounds per foot. But they tell you what it is. All right, so we said we need the 410 by 74. No, 67. There we go. 410 by 67. Let me go back out. So we have a 410 by 67, and that's our choice. That's what we're going to use. And we know that S is equal to 1200, right? And we know that I is equal to look it up. 1200 is is 267. Oh, yes, that's right. But remember we said that the steel handbook, now this is for I-beams, right? Remember what we said? For I-beams, the steel construction manual, that's this thing here. All right? It's not a small book. All right? Remember, the steel construction manual tells us to get shear, max shear, we use the average. No, excuse me, that's a tau. Tau average. Remember this? We said it's V over the area of the web. Sorry, I'm off the page. Remember that? This is per the manual, right? This is per the AISC, American Institute of Steel Construction. Now this only works for I-beams. All right? Don't get carried away. Do it all over the place. But for I-beams, this is what we're told to use. For steel I-beams, I should say, right? And they told us this was steel. So what's the area of the web? We said the area of the web is the height times the thickness of the web. So we said if we have an I-beam, this is the height, the full height, and this is the thickness of the web. And they said that's what we're going to use. We said, okay, we'll do what the book says, by the spec. And lots of buildings designed this way, so it must work, right? And so what we do again, we go back to our book here, our table. And we said for a 410 by 67, D is 410. And TW is 8.76. So we just look it up. Now, it's all based on what we selected. So it's going to be 410, that's millimeters, by 8.76, that's also millimeters, right? And now we multiply those together to get the area. I don't know what that is, but I'll figure it out here in a sec. And then we will say, we'll calculate T average is equal to our shear. What's our maximum shear? We go back to our shear moment diagram. We say the max shear is 150, right? 150. So it's 150, that's times 10 to the third, because that's kilonewtons per meter, right? So now it's newtons per meter. No, excuse me, Newton meters. There we go. It's moment. No, I need shear. Just 150 newtons. God, okay. Sorry. 150 newtons. And we're going to divide that by TWB, or the area. So the area, let's put that into meters. So that's going to be 0.41, and then it's 0.00876 times. So the area is 00359 meters. Squared. Well, that's good, because we need to get newtons per meter squared. And so that's equal to, I want to divide, and I get, see that number there? Big number, right? See how the commas help? You should always use commas. So that's 41.76 times 10 to the 6, so 41.76 MPa. And that's, of course, less than 75, which is our allowable. That's what we started with. So we've checked shear. So, gosh, we've been doing this for a while now, so let's just review the bidding. 1, find the moment and the shear. Now you need the max of both. Find max moment and max shear. How you do it's up to you. 2, size the beam. Now that either means we select, given S, we find S. This is the typical way to do it. Find S, and then pick a beam from the table, right? Now it may be that you have to size the beam, that you find S, and then you have to calculate, right? Like we did with the wood. You have to calculate the B and the H. But again, most times you're going to be given parameters like 2x4 or 2x6, or there's going to be some limitation on your selections. Because again, we're looking at this as to buying stuff off the shelf. And then the third thing is, now that we have S, we've sized the beam, now we check tau. Okay? All right. What else do we have to look at? I guess we can look at shafts. Now there's two things about shafts, right? One is with a shaft, shafts have a radius or a diameter. We're often looking for the diameter, right? So radius is equal to 1/2 the diameter. We know that I is equal to 1/4, or pi over 4 times r to the 4th, right? And if you forget, it's right here in the front of the book. But, that's a good thing to write down in case you get nervous and you say, oh my gosh, what is it? There you go. And the area, of course, is pi r squared. if we used this as a beam, then we're just going to calculate the max moment. Oh, and of course C is going to be R. The max distance from the neutral axis. Well, the neutral axis runs down the middle, and the max distance from the neutral axis is going to be the radius. All right, so it's that. So we're going to look at that outer stress. So our max moment is just going to be equal to the S, right? S over sigma allowable. And S is equal to I over C, right? I, we said, was pi over 4 r to the 4th, and C is r. So S for a round shaft is pi over 4 r cubed. Now that's for a round shaft in bending, right? So if we wanted to find R for just pure bending, right, then we would say that our maximum moment is going to be equal to pi over 4 r cubed divided by sigma allowable. Or if you want to flip it around and say, well, what is our r cubed? Solve for r cubed. You're going to take that max moment Wait a minute, what have I done here? I flipped this, didn't I? I did. Sorry. Boy, I'm silly. Sometimes, but you knew that. Okay, so this is correct though. All right, let's try that again. All right, try that again. So now we know that we said S is equal to M max over sigma allowable. That makes better sense, doesn't it? And S we said was pi over 4 r to the third. So that's going to be multiplied by 4 divided by pi, right? So that's going to be M times 4m over pi sigma allowable. And so R is going to be equal to the cube root of that. And there you go. Now you've sized your shaft, your round shaft. Let's just check our units, just to be sure I haven't gone crazy again. So what is this? This is going to be M, which is Newton meters, or pounds, inch pounds, divided by sigma allowable, which are Newton per meters squared. And so that's going to, the newtons cancel. You bring this up to the top, that's going to be meters cubed. So when I take this, the cube root of that, I'll get meters. So it works. If you think you've goofed up an equation, like I just did a minute ago, check your units. The units will tell you. All right, just like I did there to be sure I actually got it right the second time. Okay, well, that's enough of that. Have fun, and we'll talk again.